Hello everyone, welcome to the 15th lecture of this second module on analog meters. We are discussing a course on the measurement and instrumentation. In the previous lecture, we have talked about electrodynamometer kind of instruments, and we have seen that when it is operated with AC, how its deflection equation will look like. Okay. So, we have seen that say two different currents I1 and I2 were the instantaneous currents in the fixed coil and the moving coil. Okay. The instantaneous deflecting torque was given as I1 into I2 into the dm by d theta. Okay. And we have understood that what is this dm by d theta and from where it is coming. In fact, we have done a complete derivation for the deflection equation. Okay. But we have also seen the average deflection torque over a complete cycle of any AC signal, and we have seen that the deflecting torque when the equation is like I1 I2 into dm by d theta, when you try to see the average deflection, it is equal to dm by d theta into 1 by t integration from 0 to complete time period into I1 I2 into dt, where t was the time period for one complete cycle. So, let us try to see this in more practical way, or let us try to visualize this AC signal by a more practical AC signal like a sinusoidal current form. Okay. So, say if currents I1 and I2 in the AC signal that we have just seen are sinusoidal and are say displaced by phase angle phi. Okay. I1 can be given as Im1 say sin omega t, and I2 is given as Im2 sin omega t minus the phase angle phi. Okay. So, say this is I1 equal to Im1 sin omega t. I am calling again this as equation A, and I2 is given as say Im2 sin omega t minus phi, and I am calling this equation B. Alright. So, if I have to calculate the average deflecting torque, I will recall this particular equation Td equal to dm by d theta 1 by t integration over 0 to the time period for the complete cycle into I1 I2 into dt. Okay. So, if I do this, okay, I will get this Td as dm by d theta 1 by 2 pi integration from 0 to 2 pi into the current values I1, which is equal to Im1 sin omega t, into the second current I2, which is Im2 sin omega t minus phi into d omega t, right. So, this is the average deflecting torque. So, if I do more simplification, okay, I will get this as, if I try to integrate it, I will get this as Im1 into Im2 by 2 into cos phi into dm by d theta. Okay. So, this is what we got after solving. Now, consider that this I1 is equal to, okay, I am introducing another term I1, say this is equal to Im1 divided by say root 2, okay, and I2 is Im2 by root 2. So, if I find I1 into I2, this will be equal to Im1 by root 2 into Im2 by root 2, right. So, I1 into I2 should be equal to Im1 into Im2 divided by 2, right. So, if I replace this Im1 Im2 by 2 by another term I1 and I2, I will get an equation of this deflecting torque as I1 into I2 into cos phi into dm by d theta, where I1 is nothing but this peak current divided by root 2, which is nothing but the RMS value of the current which is flowing through the fixed coil, while I2 is equal to Im2 by root 2, which is again the RMS value of current which is flowing through the moving coil. Okay. So, the deflecting torque is equal to the RMS value of currents I1 into I2 into cos phi, which is the phase difference between them, okay, into dm by d theta, and this is a very important equation, and I am calling this equation C. Okay. So, we have now deflecting torque equation for the sinusoidal signals or sinusoidal current. Okay. Now, again, if I have to find the controlling torque, it will again be produced by the spring itself, and it is nothing but the k theta, and if at the steady state position I have to equate that controlling torque Tc with this Td. Okay. So, when Tc is equated with Td, the k theta value is equal to I1 into I2 cos phi into dm by d theta, or the deflection is given as I1 I2 by k into cos phi into dm by d theta. Okay. I am calling this equation as equation D. All right. So, we can say that for sinusoidal AC currents, the deflecting torque and the deflections can be determined by the product of the RMS value of the two coil currents and the cosine of the phase angle between them, or the cos phi. So, I1 I2 by k into cos phi into dm by d theta is what our deflection value is. Okay. So, we can say that the electrodynamometer type of instrument can be used for measuring both DC as well as the AC. We have derived it the deflection for AC, as well as in the previous lecture we have also derived one equation for the deflection. The coils were supplied with only DC current I1 and I2. Okay. So, when being used on AC, the instantaneous torque is proportional to I square. If you recall the case, the first slide where we have talked about in the previous lecture regarding the connection of the fixed coil with the moving coil, they were connected in series. So, we can also assume the current values I1 is equal to current value I2, and in this case this deflection will be I1 and I2 are same, say I. So, theta will be equal to I square by k into cos phi into dm by d theta. So, when being used on AC, the instantaneous torque is proportional, or can be said to be proportional to I square value. Okay. As the current varies, the deflecting torque also changes, but the average torque acts in the same direction. Okay. So, the pointer is not able to follow the torque pulsation produced by the AC current, but takes up a position where the average deflecting torque is equal to the controlling torque, as we have just seen in the equation, and the electrodynamometer type of instrument can therefore be used for measurement of both AC as well as for DC. Okay. So, instrument is, if you see in detail, instrument is initially calibrated on DC. The calibration, however, holds good for AC as well, due to the instrument's accuracy being the same for both AC and DC operations, and in the case of AC, the deflecting torque is proportional to the product of RMS value of the currents, and it denotes that particular value. Okay. So, this is about the electrodynamometer kind of instruments. Okay. Now, let us try to see how this electrodynamometers can be converted to measurement of current, can be converted into a tool which can measure current, or basically electrodynamometer ammeters. Okay. Electrodynamic ammeters. Okay. So, when you want to this kind of conversion, the fixed and moving coils are connected in series, that we have seen. Okay. And therefore, they carry actually the same current, or I1 and I2 are same. I1 is equal to I2. In this case, if you see, there is no way there is any phase difference between them, or say phi is 0 basically. So, cos phi is basically 1. Okay. So, the deflecting torque is equal to, we have seen, is equal to I1 I2 cos phi dm by d theta. When this I1 and I2 are same, I cos phi is equal to 1. Okay. Deflecting torque is equal to I square dm by d theta. Okay. So, this equation is equation E. Okay. I am calling this equation E. Okay. So, when you have this value and if you equate it with again Tc, so you have k theta equal to I square dm by d theta at steady state condition, Tc is equal to Td, okay, and therefore, this deflection theta is equal to I square by k into dm by d theta. Okay. So, for ammeters of higher capacity, the arrangement is something like this. Okay. So, in this case, the moving coil is basically shunted by a low resistance to limit the current to not flow beyond say 100 milliamp. Okay. So, there are now two separate parallel branches for fixed and moving coils, and in order that the ammeter may indicate the correctly at all frequencies, the current in the fixed coil and the moving coil must be in phase. Okay. So, this requires the time constant, which is L by R of the two branches to be equal. Okay. As otherwise the current in the two branches will not be independent of the frequency. Okay. And they may denote the erroneous values. Okay. So, the electrodynamometer movements in case of voltmeter is something like this. You can see this arrangement. Okay. This can be, I mean, you can see that this is a simple electrodynamometer, but with the extra series resistance of high non-inductive resistance. Okay. So, this is high resistance which is connected in series with this moving coil. Okay. So, this is how it is converted to voltmeter. In ammeter you have seen this small shunt values was connected. Okay. So, in this case the deflecting torque again is equal to I1 I2 cos phi dm by d theta, and I am calling this say the drop voltage was say V. Okay. Okay. This supply voltage is V. Okay. So, I1 or I2 both can be equated by V by the impedance Z. Okay, and phi is 0. So, the torque can be given as I1 into I2, okay, into dm by d phi, because cos phi is again 1. So, I1 is V by Z. So, Td is equal to V by Z square. So, V square by Z square into dm by d theta. Okay. So, this I am calling this as equation F. In case of voltmeter, this is the deflection. Okay. So, again this is the deflecting torque. This can be equated to the controlling torque, which was nothing but k theta. So, this will be equal to V square by Z square into k into dm by d theta. Alright. So, Z is the impedance of the instrument circuit, and the deflection is given as V square by kz square into dm by d theta. Okay. So, electrodynamometer type voltmeter basically is the most accurate type of AC voltmeter. However, it suffers from low sensitivity, and low sensitivity is coming from the equipment structure itself. If you have seen the construction, we have not used any core in this kind of instrument. We are using say this fixed coil only with say air core, and because of this the sensitivity of these devices are very low. Okay. Now, we have understood that how these electrodynamometers can be converted into different measuring devices, be it measurement of current or be it measurement of voltage. Okay. Let us try to understand the main source of errors in this dynamometer type of instruments. Okay. So, there are 5 different source of errors which has been identified, which can occur in this kind of instruments. The first is the torque to weight ratio, or we can say low torque to weight ratio. Second is the frequency. Third is the eddy currents, and then we have external magnetic fields, and finally the temperature changes. Okay. So, these 5 are different source of errors that can cause the reading by this electrodynamometer systems to be erroneous. Okay. So let us try to understand what we mean by the low torque to weight ratio. Okay. Now the magnetic field produced by the air cored coil is very small, as we have just talked. Okay. So basically the flux linkage per ampere in the moving coil are very less. In fact, 3 to 4% of flux linkage per ampere in the permanent magnet moving coil instrument is there. Okay. So the deflecting torque is very small. Okay. So therefore, to produce a reasonable deflecting torque, the magnetomotive force of the moving coil has to be increased. Okay. So this magnetomotive force, sometime also called MMF. Okay. So the MMF of the moving coil has to be increased, okay, to produce a reasonable deflecting torque. Okay. The MMF of the moving coil can be increased by increasing the current through the coil or by increasing the number of turns. Okay. So two ways to increase the MMF. One is by increasing the current or by increasing the number of turns through the moving coil. Okay. So both the way have their own limitations. Okay. So first let's try to understand if we want to increase the current, to increase the MMF. Okay. So if we increase the current, say beyond 150 or 200 milliamp, we have seen that for control we have added springs. Okay. So if we increase current beyond say 150 or 200 milliamp, the springs will be heated too much and you cannot rely on the spring value, or the TC will go wrong. Okay. Now in the other way, when you try to increase number of turns, if the turns are increased, the moving parts weight will be increased. So earlier, say to have say MMF value say X, you had say n number of turns in this coil. Okay, I am showing this say cross sectional view. Okay. So you have this very dense moving coil. Now to increase this with say and say number of turns were n. Okay. Now to have a MMF value of say x plus delta x, this n has to be significantly increased if you are not increasing the current beyond certain value. Okay. So when you try to increase this number of turn, okay, your moving part will be very heavy. Okay. So this, when your moving part become very heavy, the torque to weight ratio of this system decreases. Okay, because the weight is increasing. Okay, weight is increasing continuously because number of turns that you have added is increasing. It means that basically you are decreasing the torque to weight ratio. Okay, and when this kind of moving coil having low torque to weight ratio moves, basically it ends up having a lot of frictional losses. Okay. So this kind of arrangement be by increasing the number of turns in the moving coil basically increases the frictional loss, and therefore has to be a trade off between them. Okay. So this is what low torque to weight ratio means. Okay. Then there is another way of introducing error, which is by frequency. Okay. So the frequency error of this electrodynamometer type of instrument is due to basically largely due to a result of variation in the self reactance of the coil, which varies with frequency. Say in case of say consider voltmeter, electrodynamometer voltmeter. Okay. So deflection we have already seen from equation, this equation F, or we call it say equation G. Equation F is the torque equation and the deflection is say I am calling it equation G. Okay. So if I recall this equation G, the deflection was in case of voltmeter was V square by Z square and K into dm by d theta. Okay. And this Z is the impedance. Okay. This is K, the spring constant. Okay. So this Z is nothing but R square plus 2 pi FL square, right, under the root. Okay. So if you see, the value of impedance Z is increasing if you are increasing the frequency, and therefore the voltmeter tend to read low as the frequency is increased. Okay, because this Z is present over here. Okay. So therefore, in order to reduce frequency errors in voltmeters, the coil winding is made a very small part of the circuit. So this makes the inductive reactance a small fraction of total impedance, and you have Z completely as a resistance, and that is why if you see in the voltmeter we have added a highly non-inductive resistance which has a negligible L part. All right. So this is how frequency error in case of electrodynamometer tools are suppressed or at least minimized. Okay. So this means that the frequency does not affect the calibration of the instrument if you have this kind of resistance in picture. Okay. Then third source of error is eddy currents, okay, and this was the major reason that why the moving coil in the case of electrodynamometer tools have non-magnetic or non-conducting basically cores or non-conducting former. Okay. The effect of eddy currents is to produce a torque as a result of coupling between a moving coil and the adjacent metal parts. Hence, metal in the coil supports and structural parts is kept to be a minimum as possible. So coil supports, so there are several systems for supporting the coil, and the structural parts are there in the moving coil. So they are minimized to have any metal part to avoid any kind of eddy current loss. Okay. So any metal that is used to is kept away and is selected to have a high resistivity so as to reduce the eddy current induced in it, and this is the only way to reduce the eddy current induced errors in the electrodynamometers. Okay. So the metal present in coil supports in the shield produces a frequency error in the instrument as already seen in the case of MI instrument. Okay. Then the fourth one is the external magnetic fields. Since the operating field in the electrodynamometer instrument is very weak, okay, therefore these must be protected from any external magnetic field to even have worst effect on the deflecting torque. Okay. So the portable kind of electrodynamometer instruments uses metal sheets which serves to isolate the coil from any external influences or any external magnetic field influences. Okay. And the final error source is the temperature itself, where the high currents flowing in the coil is responsible for self heating kind of effect, and because of this this temperature effects are or temperature errors are introduced. Okay. So high accuracy instruments contain temperature compensating resistors which tends to neutralize the effect of temperature changes in the electrodynamometer tools. Okay. So this is some of the sources of the errors which can be introduced into electrodynamometer errors, although there are provisions or the when industry make this kind of tools they try to minimize these errors, but still some of the error persist in this kind of tools. Okay. Anyway, this instrument have lot of application, particularly we have seen a new kind of avenue which is the transfer kind of instrument, which is only this is one of the kind of instrument which can be used as a transfer instrument. Okay. So let us see some of the advantages which this electrodynamometer instruments provides. Okay. So the first is it can be used for measurement of both AC and DC, and this is one of the biggest advantage that electrodynamometer instrument provides. All instrument cannot give you this kind of flexibility. Okay. So unlike PMMC instruments, these electrodynamometers can be used on both alternating and direct current. Therefore, I can say that these tools are or this particular instrument is versatile. Okay. They have very high accuracy, so they provide good precision, especially when used as a standard instruments for calibration of other instruments like for moving iron kind of instruments. Okay. Another advantage of electrodynamometers are you are not using any permanent magnet. Okay. So we have seen the disadvantages of PMMC tools, in which we have discussed that the permanent magnet used in case of the PMMC tool itself is a biggest problem, means that there are always magnetic edging effect or temperature effect on this magnet. Okay. But in this case you are basically flowing a current through the coil, and electromagnet is in place in rather than having a permanent magnet. So this is one of the advantage of this tool, that there is no permanent magnet. So since they operate without a permanent magnet, there is no error due to magnet edging or temperature effect on the magnet strength. Okay. Then they are suitable for power measurement. So we will discuss when we will talk about wattmeters that they can also be used in a wattmeter. Okay. So another advantage that we have seen for electrodynamometers in our last two lecture discussion, that they have same calibration for AC and DC. So the instrument does not require separate calibration for AC and DC, and once you have calibrated with the DC, it can be used for AC measurement also. Okay. So they have a good frequency range, means that they can operate over a reasonable frequency range, typically in the power frequencies, at least in the laboratory conditions. Okay. And they can be used as a transfer instrument. So this is one of the biggest advantage of the electrodynamometers. Okay. So because of their accuracy and consistency, they are often used as a transfer standards between AC and DC measurements. Okay. Then there are certain disadvantages associated with the electrodynamometer, and one of the disadvantages we have already seen, that when we were talking about the electrodynamometer voltmeters, that they have basically low sensitivity. Okay. So due to the absence of a permanent magnet, the operating torque is very small. Okay. And therefore the electrodynamometers are of course less sensitive as compared to the PMMC instrument. Okay. They have high power consumption. The current required to produce deflection is basically relatively high as compared to other devices, causing a greater loading effect of the measured circuit. Okay. Then they are affected by stray magnetic field, and this we have studied as one of the source of errors. Okay. So since the magnetic field is weak, external magnetic field can introduce significant errors unless proper metal shielding is provided to electrodynamometers. Okay. The construction of these tools are very costly. So the instrument used two air cooled coils. Okay. One was fixed and another was moving, and that is what the system is more expensive as compared to PMMC tool, or if you compare it with a moving iron kind of instrument. Okay. So then another source of error was the temperature variation. So we have seen that change in the resistance of the coil with temperature affect inaccuracy, especially in the precision measurements, and the damping in this kind of instrument is usually provided by the air friction. Okay. So when you have air friction damping, this will slow down your response, as well as you may observe certain oscillations. Okay. So you can say that as compared to say moving iron instrument, the damping is poorer in case of electrodynamometers. Okay. Then they have limited use in at high temperature, so at high frequencies basically. So at higher frequencies, the inductance of the coil introduces error, restricting accurate operation, particularly in the power frequencies, and that is how they are not very suitable for high frequency measurements. Okay. So this is about the electrodynamometer kind of instrument. Okay. So we have till now discussed PMMC kind of instrument, moving iron instrument, as well as the electrodynamometer instruments. Okay. We have also discussed their torque equation and their deflection equations. Okay. So we will meet again in next week with another discussion. Thank you.